Okay, hey guys, welcome to my AP Chem project. I'm going to be going over tricky equilibrium problems. So, let's get into it. So, this first question is asking, what are the relative strengths of the acids and bases in the reaction represented by the equation above? So, we're giving KEQ. So, see that KEQ is less than 1. Therefore, this reaction is reactant favored. Okay? So if you paid attention in AP Chem, you would know that equilibrium lies on the side of the weaker base. So because KEQ is less than 1, equilibrium lies on the reactants. Therefore, ClO2 minus is the weaker base. Okay? So instantly, we can remove B and we can remove C because these two are wrong. This is not true. Okay? So now we have to figure out the strengths of the acid. So we already established that ClO2 minus is the weaker base and HCOO is stronger. It's a stronger base, okay? The conjugate acid of a weak base will be strong, okay? And the conjugate acid of a stronger base will be weak. Therefore, ClO2 minus, its conjugate acid is going to be stronger, okay? And the conjugate acid of HCOO is going to be weaker because HCOO is a stronger base. Therefore, it's going to have a weaker conjugate acid, and ClO2 minus is a weaker base, so it's going to have a stronger conjugate acid. Therefore, your answer is D. Okay. On to the next. Don't worry about that stuff. Okay, so a student prepares a solution by combining 100 milliliters of 0.3 molar HNO2 and 100 milliliters of 0.3 molar KNO2. Which of the following equations represents the reaction that best helps to explain why adding a few drops of 1 molar HCl does not significantly change the pH of the solution? So straight off the bat, we can remove A because it's just showing an ionic compound becoming a solid. Well, this is it in solution, and then it becomes into a solid. That does not relate to this question at all. So A can be removed. C can also be removed because if you write the net ionic equation, like water is not gonna, the water being made is not gonna really affect the pH. So it can't be A and it can't be C. So we have B or D. So a lot of people will pick B because it represents the dissociation of HNO2. However, that's not really a buffer because if you actually add HCl into this equation, right, into this, we know that HCl is a strong acid, right? Therefore, it's going to dissociate fully to H plus and Cl. Therefore, if we increase the reactance of H plus, okay, due to Le Chatelier's principle, this will increase your reactance, okay, because we're increasing the products. It's going to increase your reactance. So there's going to be more HNO2, which that will actually increase the pH, okay? However, if we do, let me erase this, or let me just do this actually, it's a lot faster. However, if we do H plus NO2 minus yields HNO2, when we actually add the HCl, this base right here will actually neutralize some of it, okay? That is a buffer. That is what a buffer is, okay? So therefore your answer is D. So on to the next. So on the basis of the information above, what is the approximate percent ionization of HNO2 in a 1 molar HNO2 solution? So percent ionization. Don't let this word scare you. This is a very important concept. You must know what this is. This will show up on your AP exam 100%, okay? So percent ionization is essentially how much of your reactant broke down. So let's say, this is just a random example, let's say I had 10 molar HNO2, and I got 5 H plus after the reaction once it completion. So I just do percent ionization, how much of it ionized, so 5 divided by 10 is just 0.5 times 100, just 50%. So that's how much of it broke down, okay? Very simple concept. This should be 3 points if they ask you this. So let's actually solve it. So due to this is higher than a power of 3, so we can use the assumption rule. So we can do 4.0 times 10 to the negative fourth equals 1 molar, and then your concentrations x and x, which I will simplify to x squared. So you can just do 4.0 times 10 to the negative fourth times 1 squared. Okay, so square root that. Okay, and that would give you 0.02. Okay, so now we have the concentrations of both of these, which is 0.02. So now what you do is 0.02 of how much you originally had, divide that, and that would give you 0.02. Okay, so then you do 0.02 times 100, and you get 2%. So answer is D. Easy. Okay, so the stepwise dissociation of selenous acid, H2SCO3, is represented by the equation above. Which of the following best helps explain why the Ka is so much smaller than the value of why the value of Ka2 is so much smaller than the value of Ka1? Okay. So let's go over the answers. So we have A, the Se atom, and H2SeO3 is in a higher oxidation state than the Se atom. That's not true. If you go over the oxidation numbers, this will maintain its charge, so not A. Water is more attracted to HSeO3 minus ions than to SeO3 minus 2 ions, which derives the step 2 equilibrium towards the reactants. This is not true. We know that the greater the charge, okay, and the smaller the radii, is what facilitates greater attraction to water. So this is just wrong. B is just simply wrong. So the HSeO3 minus ions produced in step 1 are asymmetrical, but the SeO3 minus 2 ions produced in step 2 are symmetrical. This has no meaning. This is just wrong. Well, it could be right, but it just doesn't relate to the problem at all. Especially if you study equilibrium, you know that this does not matter. Now we have D. Removing the first H plus from H2SeO3 requires less energy than removing the second. So this is the right answer. This is essentially the same principle of ionization of energy. The more you remove, the higher it'll be. So let's say you ionize sulfur. I'm just gonna make up a number, 100. You're gonna ionize it again. It's obviously gonna be higher. You're gonna ionize it again. It's obviously gonna be higher. So same principle. So D is your answer. And yeah, it's gonna be harder to remove. So it's gonna be less to dissociate. Therefore, your concentration of H as well is going to be smaller, which represents the small Ka value. Alright, my bad, I'm kind of sick, but so next problem, HCHO2 is a weak acid. Ka is given to us. This dissociates in water according to the equation above. Which of the following provides the best estimate of a pH of 0.5 and identifies the species at the highest concentration? Okay, so this is the same thing as we did here. You can just assume again. So let's just do this quickly. So 2 times 10 to the negative fourth times 0.5 squared. That is going to give you times 0.5 root. That's going to give you 0.01. If your concentration of H, so negative log of 0.01 will give you 2. So your pH is 2. So A is gone, B is gone. Now, species at the highest concentration. Some people will pick C, but you know, if you just do the math, 0.01 is obviously a lot less than 0.5. So HCHO2 will be the higher concentration. So it's gonna be D. Alright, cool. Now we're doing an FRQ. Okay. This FRQ is pretty good example on what they'll ask you on the AP exam, and I don't think it's gonna get more complicated than this. So if you find this easy, then you should be good. Okay, so in an aqueous solution, ammonia reacts as represented above. In 0.0180 NH3 aqueous at 25 Celsius, the hydroxide ion concentration OH is 5.6 times 10 to the negative 4. And answering the following, assume the temperature is constant at 25 Celsius and that the volumes are additive. So A, you write the equilibrium constant expression for the reaction above. Very easy. Products over reactants. So OH concentration NH4. Don't include water in your KP, in your KB expression. So just a concentration of NH3. So if you got that, give yourself a point. Let's go over the next one. Determine the pH of a 0.0180 molar NH3. So very simple. We already have our OH concentration, so we can literally just do the negative log of 5.60 times 10 to the negative 4th, which that will give us our POH, not our pH. So just 3.2. And we want the pH, so we do 14 minus 3.2, which gives us 10.7. So your answer for B is 10.7. So next, determine the value of the base ionization constant Kb. So if you read the problem, you know that this is at initial. You need to figure out what that value is at equilibrium. So we already know our OH is 5.6 times 10 to the negative 4. If you do an IC table, you're going to know that you just do the 0.0180 minus x, which if you do an IC table, you're going to get 5.6 times 10 to the negative 4th. Some people might need to write an IC table, but some people just know that you have to subtract your initial by your x's, which is your concentrations of your products, which is already given. So you can just do your initial minus the concentration, and that will give you 0.01744, I believe, if I did that right in my head. Yeah, 0.01744. So that's your new concentration of NH3. So now you can plug this into the equilibrium expression that you guys already wrote earlier. So 5.6 times 10 times 10 to the negative 4. And you can just assume that your acid concentration will just equal the concentration of your base, because it's a 1-to-1 molar ratio. So you can just do 5.6 times 10 to the negative 4 again for your concentration of your acid. Then you divide that by your new molarity that you just solved for at equilibrium. So 0.01744, and that's going to give you an answer of 5.6. You can square it. You type this into your calculator, so you get the same answer. 1.79 times 10 to the negative 5th is going to be your answer. I'm just going to write it right here. because you're actually going to use this KB value to solve one of the next questions. So I'm just going to leave that here and erase the rest. So give me a second. Okay, so now we have determine the percent ionization of NH3 in 0.0180 molar NH3. So again, same concept as this multiple choice question that we went over. Remember, percent ionization is how much broke down divided by how much it had originally. So again, it broke down to this much, so just do 5.60 times 10 to negative 4 divided by 0.0180, and that will just give you 5.6 negative 4 divided by 0.0180 times 100. Make sure you multiply that by 100, but you get 0.03 times 100, which that will just give you 3%. Easy. They will definitely ask you this in a multiple choice question, FRQ. Make sure you guys know this though. This, like, I will bet, wait, right here, I will bet like my life savings that this will show up on your exam. So make sure you guys know this, okay? So let's erase. Now we're on to E. So as I'm erasing, let me explain E. So determine the volume of, in an experiment, 20 milliliters sample of 0.0180 molar NH3 was placed in a flask and titrated to the equivalence point and beyond using 0.0120 molar HCl. So determine the volume of 0.012 molar HCl that was added to reach the equivalence point. You can just M1V1 this, but remember that if this is not a 1-to-1 ratio, you're actually going to have to convert your moles. I'll explain what I mean by that in a second. So 0.02 times 0.018. This will give you your moles, and then you're just going to divide that by 0.0120, and that's just going to give you 30 milliliters. But for future reference, if this is not 1-to-1, you're going to have to take this answer and do a factor label problem to get how many moles of your other, like for example, if this was like NH3, like if this was like 1 and this is like 2, you're gonna have to do like 1/2 to get your new amount of moles, and then you divide it by your molarity, and that'll give you your answer. So that's just for future reference if they ever ask you that. Personally, it's always been 1-to-1, so you can just M1V1 it. So yeah. Let me just make sure that was the right answer. 30 milliliters. Okay. Next, determine the pH of the solution of the flask after a total of 15 milliliters of 0.0120 HCl was added. So we can just do 0.015 times 0.0120, and then that will give us, I believe, 1.8 times 10 to the negative 4th moles of HCl. Let me just make sure that is correct. Yep. So that's how much we are putting in. So let me erase this so I can explain this better. So this is the flask. Let's just say like this is your flask, right, of your stuff. You know, this is not the best drawn, but it's fine. We originally had 20 milliliter sample of 0.0180. So let's write that. Let's figure out the amount of moles in that. So convert milliliters to liters times 0.0180. That's going to give us 3.6 times 10 to the negative 4th. Okay? So we have this many moles in our flask. Okay? We already put this many moles. Well, we're putting this many moles into this flask. It's going to neutralize 1.8 times 10 to the negative fourth of this. Therefore, we're only going to have 1.8 times 10 to the negative fourth left of NH3, and that will create another 1.8 times 10 to the negative fourth H ion and your base, okay? So then this is known as the half equivalence point, and we know at the half equivalence point pH equals pKa, okay? Or vice versa, pOH. Yeah, pH equals pK. So you can use your Kb value, okay? So negative log of your Kb value, okay? That will give you negative log of 1.79 times 10 to the negative 5. That'll give you 4.7. Okay. 4.75, we're going to say. Oh, I don't know why I did that. Oops. I'm going to have to cut that out. Okay, I don't know what happened. My thing just like crashed out. We're just going to go back to where I lost all that. So what we were doing was the negative log of the KB. So 1.79 times 10 to the negative 5. That gave us 4.75, and then we're just gonna do 14. This gives us your pOH. So then just do 14 minus 4.75, which is, I believe, like 10 point or 9.3. It's gonna be your answer. Yeah, give me a second. Yeah, I don't know why my thing crashed. Sorry about that, but we're just gonna continue. So we have last one. Determine the pH of the solution in a flask after the total of 40 milliliters of 0.0120 HCl was added. So let's just figure out the amount of moles again. So let me just erase this. It's kind of hard to erase because my screen is black, but so yeah, same process. 0.06 times 0.0120 will give us, I think it's like 4.8 times 10 to the negative fourth, and then we already had 3.6. So again, in the flask, right? That's gonna leave 1 point. We're going to neutralize all that, and that's just going to leave us 1.2 times 10 to the negative fourth left, because we originally had 3.6 times 10 to the negative fourth, and this will neutralize all of that. So we are past the equivalence point, so no more reactant left. So this is all gone, and we're just left with 1.2 times 10 to the negative fourth of your OH. So then we're just gonna do that amount of moles divided by the total liters of the whole entire thing. So we added 40 and it already had 20, so just 20 plus 40 to 60, so 0.6 liters left of your concentration of your HCl. You don't have, so then you do the negative log of 0.002. Now this won't give you the pOH anymore because there's just acid now, like we're doing the acid, so HCl. So now there's HCl left now, so there's no point doing pOH. This will give you your pH instantly, so negative log of 0.002, which is then 2.69, and that's your pH. And that's it. Thank you for watching.